Welcome everybody to the second week in Discrete Mathematics. So this is the sixth lecture and we will be starting our short part of this course which will be dedicated to mathematical proofs. Now, what are mathematical proofs? Or in other words, if I give you a statement, how do you check if the statement is correct? Now you must have faced this problem many times in your school or college or even in life. Now there are two ways of going about proving this theorem or of proving a statement. For example, consider this following statement. For all n, the integer n square minus n plus 41 is a prime number. So this is a statement I claim. Now if I ask you to check if the statement is correct, how will you go about it? So there are two ways of checking if the statement is correct. The first proof technique is what we call as empirical or experimental proof. That is, we would like to try this particular statement or any statement on a number of cases, and if the statement holds for all the cases for which we have tried, we would say the statement is correct. So this is one way of going about it. The second way is the mathematical way, or in other words, use mathematical reasoning to prove the statement. Here, we would like to go step by step and ensure that we have a full proof of that. Now, to start with, let's look at experimental proof or empirical proof of that statement. So here is the statement. So for all n, the integer n square minus n plus 41 is a prime. Now how will you go about it? Of course, you want to check for various integers. For example, in the empirical proof, say put n equals to 1, you get n square minus n plus 41, this is 41, which is a prime. Great. If n equals to 2, once again, n square minus n plus 41, this is a 43, which is also a prime. N equals to 3, you can check it that again we get n square minus n plus 41 which is equals to 47, which is again a prime. Okay, great. One more step. Again, if n equals to 4, you can again check that the equation equates to 53, which is again a prime. And if you want, you can keep on checking. For example, n equals to 5, 6, 7, 8, 9, 10, so on. Go up to 20, 30, 40, and you will see that the statement is correct. So, from this experimental proof, we can conclude that the number n square minus n plus 41 is indeed a prime. It's always a prime for all n. Why? Because we have tried it out on some cases, and those cases have revealed that it is a prime. So many times in our real life, we do make such kind of proofs, where we, to check whether some statement is correct, we sample or we test out this statement on a small number of points or instances, and if for all of them we get the right solution or we prove the statement, we are happy, and in that case we say that, oh wow, this statement is right. But in mathematics, that might not be the best way of going about it. So, for the case of empirical proofs, it has, of course, some advantages and some disadvantages. So let's see what are the advantages and disadvantages. So for the empirical proofs, the first advantage is of course the fact that it is easy to give a proof. It is easy because we just have to, it is easy to give a proof. It is easy to check if a statement is correct or not on a finite number of instances. But there is a downside to it. The downside is that they are not 100% accurate. Now it's obvious why. Because for example in the earlier statement, we have just tried out n. The statement n squared minus n plus 41 is a prime on just a finite number of points. It is humanly impossible to test it out on infinite number of points. So, there might be a mistake somewhere. There might be some n for which is not true. And in fact, that's what happens. For example, if you take n equals to 41 in that example, we do get n squared minus n plus 41 is 1681, which is 41 squared, which is clearly not prime because it's the square of an integer. So while we had made some experiments and for most of the instances we did get this statement to be correct, yet the statement was not correct. We don't like this kind of a proof to exist. Of course, if you are betting your money on something, you'd like to be 100% accurate. And believe me, mathematics is something where you bet your money. For example, you are using your credit cards online, you are using your various bank statements, bank things, so on and so forth. They're all online. All the security of all these internet transactions are based on some mathematical statements or mathematical theorems. And unless they are 100% accurate, you don't want to risk your money on it, right? So if I say that your credit card is 100% safe, I would like to say that the security of this whole system is based on a theorem for which I have a mathematical proof. If I say that I have an empirical proof or an experimental proof, will you be satisfied with it? Because all you know is that for some particular instances, this whole security might break, and in that case, you will lose all your money from your credit card or bank or whatever. So, similarly, say when you are going on a flight, and I would like to say that, okay, the security of the flight, or the safety of the flight, or the fact that these things work, is based on some mathematically proved statement. You don't want to risk your life on theorems for which we have an empirical result. So in other words, we would like to have a mathematical proof all the time for every statement. So the pros and cons of the mathematical proof is that, of course, the advantage is it is 100% accurate. There is no chance of any error in the deduction. So say completely everything is perfect. There is no chance that you have made a mistake. Because it's a proof that follows from mathematical reasoning. The disadvantage is, of course, the fact that it is hard to prove. It isn't the easiest proof to come up with. While the empirical proofs are easy because you just have to test it out on some instances, mathematical proofs can be extremely complicated. You might remember these things from your high school or other places where you have to come up with very creative ideas for getting a mathematical proof. But all said and done, at the end of the day, Mathematical proofs are always better than empirical proofs because they give you 100% guarantee. And we would like to have a mathematical proof all the time for everything. In this course, we will be doing only mathematical proofs and there will be no empirical or experimental proofs at all. We will show you how to go about proving a statement mathematically with full logic, full reasoning, so that it is 100% accurate when you prove it. No one can challenge it. No one can say that it's not a full proof. So to come up with different techniques of mathematical proofs, we will be using propositional and predicate logic, this thing that we have developed in the last week. So we will use them to understand different mathematical proofs so that using them we can come up with solid proofs of them. So to recap, what is propositional logic and predicate logic? Now in propositional and predicate logic, we say that every statement is either true or false. There are connectives, namely and, or, not, implies, and if and only if. A statement can have an unidentified or undefined term called a variable, but every variable has to be quantified using either the quantifier for all or there exists. Now here is the most important thing of propositional logic. Two logical statements are said to be equivalent if the two statements answers are exactly equal on every input. And this can be checked either by using the truth table or by reducing one to the other by using some standard rules. I hope that you remember all this, the propositional logic and predicate logic that was done last week. So now moving on, how do you use propositional logic for designing proofs? Now, as I told you earlier also, a mathematical statement or any statement for that matter comprises of a premise, and when the premise or assumptions are satisfied, the statement deduces something. Or in other words, it is of the form A implies B, where A is a set of assumptions and B is a deduction of the mathematical statement. Now, how to check if the statement is correct? That is, how to check the statement A implies B is correct? And if it is indeed correct, how do you prove the following? Prove the statement A implies B? Now, depending on whether A or B can be split up into smaller statements, we would like to break up the problem of A implies B into smaller problems and apply different kind of techniques to them. And if you can finally end up proving A implies B, it is only then we will say that this statement is a theorem. Now, there are different proof techniques for attacking this problem of A implies B. Different mathematical proof techniques. I have listed down some of them. Constructive proof, proof by contradiction, proof by contrapositive, induction, counterexample, and existential proof. We will go over one by one and see the different proof techniques. Again, I repeat, all of them are mathematical proof techniques and none of them are empirical or experimental proof techniques. So finally, all of them will give you a 100% accurate proof of a theorem. But given a problem, the biggest question is which of the proof techniques to apply. So even before I introduce you to the proof technique, let me tell you this fact, which approach to apply. And the thing is that it of course depends on the problem. Depending on the problem, you can decide, or you have to decide which one will be the most suitable one to apply. Which proof technique will make your life easiest? As I told you, sometimes the problem can be split into smaller problems, each of which can be tackled easily, individually. Sometimes viewing the problem in a different way can help you to tackle the problem. Now, whether to split a problem or how to split a problem or how to look at the problem is an art in itself, and that is what has to be developed by you. In this course, we will be giving you all the tools, that means all the techniques of attacking the problem. We will be doing a number of problems as to understanding which approach will be the right approach to do. We will give you some thumb rule, but at the end of the day, it is you who has to have the creativity to understand how to split a problem, how to go about attacking a problem. So although there are some rules, at the end of the day, it is your skill that has to be developed with a lot of practice. Now let's jump into the set of proof techniques. Now the simplest way of splitting a problem is when you have A implies B and the B can be written as C and D. The propositional logic statement that kind of guides us here is this thing which says that if B can be split up into C and D, then A implies B, which is of course same as A implies C and D, is same as A implies C and A implies D. So in other words, if I give you this problem B, and I give you the problem A implies B, and you can split up B as C and D, then it is good enough to first show me that A implies C and then showing me A implies D. Here is an example where we split the big problem into two smaller problems, namely A implies C and A implies D. For example, consider this problem. If B is an odd prime, then 2b square is bigger than or equal to b plus 1 whole square, and b square is congruent to 1 mod 4. Here I hope that you remember the notations of number theory that was introduced in the first week lectures. Now, if this is the problem to do, just try to understand which is the B here. Then B is, or if A, as an A implies B, so B is an odd prime. If this is A, then, and we have this part, 2b square is greater than b plus 1 whole square, and b square is congruent to 1 mod 4 is b. Now clearly here, the b can be split into two parts, namely this part and this part. And that's what we will be doing. This will help us to solve it. So if this is C and this is D, we can have A implies C and A implies D. Thus, this problem can be split up into two parts, namely, first part, if B is an odd prime, then b square is congruent to 1 mod 4, and if b is an odd prime, then b square 2b square is greater than or equal to b plus 1 whole square. Here are the two parts that we have got. So a big problem has been split up into two smaller parts. Now, so that means that we can handle each of these small problems individually. So let us start with the first part. That means we can handle the small problems individually. Now, before we move on to solving these two parts, let me tell you another trick. Namely, sometimes the assumptions are redundant. That means some of the assumptions that have been told are not necessary. For example, so in that case, we can throw them. If the assumptions are not necessary, we can just throw them. That means if A implies B, then A and C also implies B. This is the statement that we can prove, that A implies B implies A and C implies B is also true. So if A and C is the given assumption, but I am able to prove that A implies B, that means the C was a redundant assumption and we can throw it. And in that case, A and C implies B for this statement is good enough to prove this statement A implies B. Now, throwing away redundant assumptions helps us to clean up the problem and get more focused in attacking the problem. It helps us to understand what is the important problem. Although it is not the easiest thing to understand beforehand which assumptions are needed actually. So which assumptions are needed is something to guess using your own intelligence. This will of course come with some practice, and sometimes you can understand by trying to solve this problem. You can understand which of the assumptions to be thrown at. So for example, let's take our problem which we have split into two parts, first part and second part. Now if we start with the first part, which says that if B is an odd prime, then B square is congruent to 1 mod 4. Here, an odd prime has many properties. The question is that which properties of the odd prime do we need to use in this proof? Now, what is an odd prime? A prime number which is odd. So 2 is a prime, but that is an even prime. But any other prime other than 2 is an odd prime. So 3, 5, 7, 11, 13, 17, 19 and so on are all odd primes. Now in this problem, it so happens that we only need the property that an odd prime is bigger than or equal to 3. We don't need any other thing. We don't need a property of prime at all other than the fact that it is bigger than or equal to 3. So thus, this first part is same as or is as good as proving, or it is sufficient to prove that if B is a real number greater than or equal to 3, then B square is congruent to 1 mod 4. Similarly, let's go to the second part. It says that if B is an odd prime, 2B square is greater than or equal to B plus 1 whole square. Now again, here B is an odd prime, so which properties of the odd prime should be used? And in this particular problem, all we need is b is an odd number or odd integer. That's all we need. So, in this case, it is sufficient to prove that if b is an odd integer, then 2b square is greater than or equal to b plus 1 whole square. So thus, the main problem that we had has first we split up into two smaller parts, and then we showed that we can remove some of the assumptions and get to more precise statements, which will be hopefully easy to prove. So here are the two parts. Problem first part, if b is a real number greater than or equal to 3, then b square is congruent to 1 mod 4. And the second part, if b is an odd integer, then 2b square is greater than or equal to b plus 1 whole square. Now, how do you go about proving this statement? So, we will give constructive proofs for this problem. Now, what do we mean by constructive proof? So, constructive proof is something where to prove b from a, we use either of the two techniques. Namely, we first come up with the direct proof, that means we take a, we play around with it, we make some changes and we get b out of it. We call it direct proof. And second proof is that if we can split up the problem into even smaller statements depending on the assumptions of a. In the next video lecture, we will be solving the problem using the direct proof technique. We will solve both the problems. This week, we will be spending mostly on time on proof technique using constructive proofs, namely direct proofs and case study proofs. We will be also be going a little bit into proof using contradiction, which is another very powerful proof technique.